Hello, this is Dr. Joseph, and we're getting ready to record the final video of the semester. And this is about integration in polar coordinates. Okay, so our goal is to calculate area of a polar curve. So let's just remember how we calculate area in rectangular coordinates. Um, of course, the rectangular coordinate system is a grid. And so equations in rectangular coordinates that kind of are naturally easy to compute areas using rectangles. So that's what we did with Riemann sums when all our functions were y as a function of x, or sometimes x as a function of y. And it's worthwhile to think about what sort of a grid. So remember with polar, our R equals a constant curves are concentric circles centered at the origin, and then our theta equals a constant curves are lines through the origin at different angles. Um, so the shape that is cut out in between two angles and at a given radius is a sector of a circle, a little piece of pizza or pie. Um, So think back, what is the area of a shape like that? It's 1/2 r squared theta. So that will be, that formula will show up in our integral, whereas before we just had area of a rectangle is length times height. Um, so we didn't notice it as much with rectangular. We're going to notice it a little bit more now. Um, so the idea to find the area of a polar curve is that we're going to have an interval of angles. So we'll go from angle alpha to angle beta. And the setup is that we're given a function which is r radius as a function of theta. So the curve, our actual function graph is here. And then in between those two angles, we're looking at this shaded region. So that's the area we'd like to compute. And of course, integrals are limits of approximation. So first we have to understand what the approximation looks like in order to understand the formula for the actual integral. So cutting our interval of angles up into subintervals cuts the region up into little wedges. Notice at this point they still have their curved um, ends. When we do our approximation, we're going to be using actual sectors of circles. And so just like with Riemann sums for y as a function of x, we have to choose um, values, x values, to take values of the function for the heights of our rectangles. That's what we did before. Now we have to choose thetas in each subinterval of angles to decide which R value to use for that sector. So you can use left endpoint, right endpoint, midpoint, really any point that's in that interval. Doesn't matter that much. It'll change your approximation, but with the integral we'll eventually do, it won't change the value of the integral. So that's what this theta star is. That's just some value of theta in this subinterval. And then the area of that particular sector is 1/2 times the radius for that theta squared times your change in angle. So my change in angle is whatever the angle for that little wedge is. And then maybe I choose an angle that's like a third of the way up. That's my theta star. So then the sector going through that would be like an actual sector like this. That will give me an approximation of the true, more curvy area for that subinterval. So here's a picture of that. A little bit hard to see that they're curved, but these are actually parts of a circle using different radii for each one. Notice like this is the theta that they used for that sector, for example. Um, so the sort of, I want to say red area here is the approximation that we would get using a Riemann sum with four sectors. Um, and you can see that's a pretty good approximation for this curve. Um, so the approximation, you're just adding up areas of sectors. Um, so we're not going to ask you to do this, but it's important to see this because it helps you to understand where the integral comes from. So notice, for example, this delta theta in the approximation, that will become the d theta in the integral as we take the limit as n, the number of sectors goes to infinity. And remember, that's also the same as saying that the widths, the d delta thetas are all going to zero. So they're getting skinnier and skinnier, and that makes the approximation get better and better. So this is the formula that you'll be using, and it has some hypotheses here. It says we want a function of the form radius is a function of angle theta, and that should be continuous. That's a familiar requirement for integrals. We also want it to be non-negative, and we want the angles, their breadth to be no more than 2 pi. So then the area of the region bounded by those angles and the curve r of theta is going to be 1/2 times the integral of r of theta squared d theta. Um, Evaluated from alpha to beta. So just to note this thing about the angles not going more than once all the way around is to make sure we're not like double counting area. Um, if you did a circle from 0 to 4 pi, that would just count the area twice, right? Is the idea. So we don't want to overcount. And this thing about R being non-negative is because we want the geometric shape that we're looking at to actually lie in between those angles. You can make sense of it when R is negative. And we'll see an example like that, but you have to be a little bit careful. So this is just like a very precise statement that you have to scratch your head a little bit if you're working with negative R's. Um, so let's see an example. Set up but do not evaluate an integral that calculates the area enclosed by one loop of the four-leaf rows. R is equal to cosine of 2 theta. Okay, so we may be given a graph when doing problems like this, but um, basically we can expect this to look a lot like R equals sine of 2 theta, which we calculated in the last video. We sketched it out. Um, and basically it's going to look like that, but be shifted a little bit. Um, and so one loop here is going to correspond to the portion of the graph in between two consecutive zeros of cosine of 2 theta. So remember, when r is 0, that means we've come back to the origin. Um, and so in between two consecutive zeros, that's going to be one full loop of this rose shape. So we'll look at the graph in a minute, but even without that, let's try to guess a correct range of angles to use. So I'm setting my r equal to 0. And this is cosine of 2 theta, so let's just sketch cosine of theta because we remember how to do that. And then say, well, that's 0. Two consecutive zeros would be when theta is negative pi over 2 or pi over 2. Um, so here I've got cosine of 2 theta. So that means I want 2 theta to be either negative pi over 2 or pi over 2, so that the cosine of those is 0. And that means that theta itself is minus pi over 4 or pi over 4. So my integral is going to be 1/2. Don't forget the 1/2 from minus pi over 4 to pi over 4. And I just take my r function, cosine of 2 theta, and square it, d theta. So that's it. And here's the graph. Um, Second screen. Okay, there's the graph. And oh my gosh, I, I'm busy. I'm doing work. Okay, so from minus pi over 4 to pi over 4, that's like an angle of minus 45 to pi over to 45. So basically we're in between the graphs of y equals x and y equals minus x. Let's make those both black. And I'm going from minus pi over 4 to pi over 4 is the way I set up my integral. That's not the only possible answer, but that would calculate this right rows here. Um, so in your homework, you will be given some trig identities to help you with those integrals because they're not super obvious how to do. Um, for now, I will just use Desmos to tell us the answer. So it's 0.39 is the area there. All right. And we have one more example today. Okay, so consider the polar curve r equals 2 plus 4 sine theta. Find the values of theta where the inner loop begins and ends, find the area of the inner loop, and then find the area of the bounded region that is outside the loop. So for this one, we're definitely going to want to graph this, which I have already done. And here's the graph in blue. Now, when r is 0, sine of 0 is 0, so r is 2. So we're actually starting at this point 2 comma 0 right here. Why don't we make this different color, a bit bigger? Whoa, that's too big. Okay, so that's our little point. And by the way I do this, use the slider C for theta, and then this is R times cosine theta, and this is R times sine theta, because X is R cosine theta, Y is R sine theta. That will traverse the curve. And I've got it going from 0 to 2 pi exactly once. So let's see what happens. Went around the outer loop, then the inner loop, and then to its starting point. Um, so we will solve for this in a moment, but to cut to the chase a little bit, that inner loop is going to be this purple curve from 7 pi over 6 to 11 pi over 6. And um, one way to get the outer loop is to go from minus pi over 6 to 7 pi over 6. Um, all right, so that means from minus pi over 6 to 11 pi over 6, I traversed the entire thing once. And let's shut that off and that off. 7 pi over 6 to 11 pi over 6 is just the inner loop by itself. So if I integrate over that interval, that'll give me the area of the inner loop. Now, the outer loop, um, well, what I'm asked to find is the area in between the two loops. So if I went all the way, negative pi over 6 to pi over 6, um, maybe let's watch this again. When R is, for example, before we get to 7 pi over 6, here, the little wedges that I use in my approximation, they will include the inner loop, which is sort of bad if I just want the area in between them. So we just have to understand how what the integral is calculating, right? So it's calculating all that area. So if I did one full revolution, 0 to 2 pi, or I'm going to do minus pi over 6 to 11 pi over 6, that will compute the full bounded region here, including uh, the inner loop. So that full shaded area in green. I already said how to get the inner loop, and then to get the area in between them, we just subtract. All right, so I'm going to switch back to the iPad one last time and work out expressions for those integrals. So we have to use our knowledge of the graph a little bit here. But again, I am looking for two consecutive zeros to answer part A here. Um, and just uh, keeping in mind the shape of the graph a little bit. So I guess, yeah, it's a combination of using the graph in this case that would be given in a problem like this because this graph would be hard to graph by yourself, but with no technology. But a combination of them allows me to deduce exactly what's going on. All right, so anyway, we get sine theta is negative 1/2. So -1/2. So I want a reference angle of pi/6, and I want to be in quadrants 3 and 4. Here and here with a pi/6 there. So that would be 7 pi/6 and 11 pi/6. Yay. Okay, so that's our answer for where the inner loop begins and ends. Find the area of the inner loop. So that'll be 1/2. And we already kind of said how to do this. So I take my full formula for r, 2 plus 4 sine theta, parentheses, squared d theta. That's our answer. And then I'm not worrying about finding the area right now. I'm just writing the integrals down. And C, find the area of the bounded region that is outside the loop. So that's the region in between them. Um, so it's a big, I don't know. I don't know what's big or small, but both both loops together is we said minus pi/6 to 11 pi/6 and the same function. So if we call our answer to part B, B, we call our answer to part C, C, well, it's not our answer to part C, but what we just computed, call that C, then in between the loops would be C minus B. So that's just the same principle we've been using, um, larger region minus smaller region. Yeah, so like I said, there will be some identities given in the homework to help you compute some of these integrals. To compute this one, your first step would be to actually square 2 plus 4 sine theta, right? So that's 4 plus 16 sine theta plus 16 sine squared theta. Then you can split up the integral and you know how to do this and this, but for the sine squared term, you will need a trig identity um, that is given to you in the homework. All right, so that's all. Happy calculating.